So this is the first of 2 videos and lessons on the chain rule, which is arguably the most important differentiation rule we'll look at in this course. And that's because it allows us to combine different functions together. Essentially, the chain rule shows us how to differentiate a composition of functions. And remember, a composition of functions, as you can kind of see here, is when you have one function inside another. And to kind of summarize it, if you want to find the derivative of a composition of functions, g of x inside f, the idea is we differentiate the outside function first, in this case f, with respect not to x, with respect to g of x. And then after that, we multiply by the derivative of g of x with respect to x. All right? And before I talk more about any of that, let's just show you. It's one of those things that if we just show, I think it makes more sense. So I want to differentiate this. Okay, a to the power of x equals 1 plus x squared, all to the power of 99. And one way of looking at this is a quadratic function inside a polynomial function of degree 99. So the first thing I want to do if I want to differentiate this is think about what's the outside function. And the outside function is this polynomial of degree 99. I want to differentiate that, leaving the inside function alone. Or what we're really doing is we're differentiating everything you see here with respect to not x, with respect to 1 plus x squared. In practice, I know that sounds complex, is I use the power rule. So I have 99 times 1 plus x squared. That's been left alone to the power of 98. What you see here is the derivative of a of x. This is the derivative of 1 plus x squared, all to the power of 99, but with respect to 1 plus x squared, the inside function. All right, so I want in the end the derivative with respect to x. So what I need to do now is multiply by the derivative of the inside function with respect to x. And the derivative of the inside function is 0 plus 1 plus 2x. Or 1 plus, oh actually I'll do it in 2 steps. So now I want to multiply this by the derivative of 1 plus x squared. Which again, I've already stated what that is. So this is 1 plus 2x. So this here is a derivative of the inside function with respect to x. Now, at this point, I could clean this up a bit, but I don't really care about that right now. So there's my derivative. Okay, so essentially what I did is I found the derivative of the outside function and left the inside function alone. And then I multiply that by the derivative of the inside function. And you kind of work these layers. And you always have to think about what's working from the outside in. And if there's 3 layers, you have 3 steps. If there's 10 layers, you have 10 steps. You always work from the outside in, each time leaving the function inside alone. What you're really doing is you're not differentiating with respect to x each time. You're differentiating with respect to what's inside. But like I said, it makes much more sense if we just keep looking at more examples. And notice I will spend 2 videos on this. So next, I have tan squared of n theta. Okay, and I want to differentiate with respect to theta. I know that because I have b of theta here. So what's going on here? Well, one thing that's helpful is to rewrite this to make it really clear as tan of n theta all to the power of 2. So I haven't differentiated anything. But perhaps this makes it more clear how many layers they are and the order of the layers. There are 3 layers of functions here. The outside layer is the quadratic layer, power of 2. The next layer inside that is the tangent function, and the very inside layer, the third, is a linear function, n times theta. And so there's 3 layers here. And so if I want to differentiate this, first I need to start with the outside layer, which is 2, leaving tan of n theta alone, and I'll put brackets around it. I don't really need it. The power of 1. So there's my first step done. Next, I differentiate the second layer. The second layer is the tan of n theta, but again, n theta is a linear function inside a tangent function. So I next differentiate the tangent function with respect to n theta, or just leaving n theta alone. In principle, it's the same thing. And so the derivative of secant theta, so the derivative of tan theta is secant squared. And so the derivative of tan of n theta is going to be secant squared of n theta. But I still have one more step. Now I have to find my last step is to differentiate the very, very inside function. And again, n theta is inside the tangent function, which is all inside this quadratic function, power of 2. And so the derivative of n theta with respect to theta is n. And again, it's really important to keep realizing what we're differentiating with respect to, because if there was an n right here, then that would change things slightly. Theta would be like our constant, n would be the variable we're differentiating with respect to. But now I'm done. So notice my 3 layers here. The quadratic function on the outside, the tangent function, which I differentiated second in the middle, and then the linear function that I differentiated last on the inside. And again, I could clean this up a bit. For example, I could multiply 2 times n and put 2n or something. But that's what I'm, again, not really too concerned about. All right, so I think I have 2 more examples here. Yeah. Let's look at this, c of t. Okay, so I'm differentiating with respect to t, because again, e is not a variable. One thing I would do is anytime I see an expression like this, I would write it with a negative exponent, because then I can use the power rule. Otherwise, I have to use the quotient rule. And so before I differentiate, let me just write this as 1/2 e to the negative 2t. And again, if we're not thinking of this fairly soon, we want to think of this. I mean, the more you can use the power rule, the better. And it's a lot easier to use the power rule than the quotient rule, although they are, in the end, would all be equivalent. Again, I haven't differentiated anything yet. Now I want to start differentiating. Okay, so I want to find c prime at t. All right, so what do I have here? I have 2 layers of functions here. This constant of 1/2 doesn't really affect things much. So the most important thing is I have an exponential function, and on the inside of the exponential function, I have a linear function. So I have 2 layers. So first I need to differentiate the outer layer with respect to the inner layer, or differentiate the outer layer, leaving the inner part alone. And so the derivative of 1/2 e to the negative 2t so far is 1/2 e to the negative 2t. Remember, the derivative of an exponential function with a base of e is unchanged. That said, now I have to multiply this by the derivative of the inside function. And the derivative of the inside function, which is a linear function, is negative 2. And so keep in mind, at this point, again, I'm not too concerned about going forwards. It is pretty nice to just cancel out the negative 2 and the 1/2. So in the end, I get negative e to the negative 2t. That's it again. A common thought students have at this point is, hey, didn't you say that e to the power of x, the derivative of e to the power of x, is completely the same? And yes, I did. That's when you have just an x here. But as soon as you have something else, if you have the derivative of e to the power of ax, this is not the same as e to the power of ax. What it is the same as is e to the power of ax times the derivative of ax, which in this case is just a. So again, this idea that it's literally exactly the same is true when you have e to the power of x. Nothing else inside the exponential function. And if you go back to where that was first introduced, you would have noticed, actually, I said a common mistake. In fact, let's see if I can actually find it. Let's go on a journey back in time. Where is it? Was it here? Yeah, here it was. Okay, so notice my little note right here. The derivative of e to the ax is not the same as e to the ax. We can now say it is the same as this times a, the derivative of ax. Okay, but I don't want to start messing up our notes. So let me get back to this. Last question. What I'd highly recommend you do at this point is pause the video in a moment, but first think about how many layers are there here. Example, this question had 2 sort of layers to it. This had 3 layers to it. Tangent on the outside, sorry, power of 2 on the outside, tangent in the middle, a linear on the inside. How many layers does this have? If we understand some aspect of this, we're definitely going to make a mistake. Okay, I wouldn't worry so much about trying to differentiate it. Just how many layers are there? And so I recommend you kind of pause the video. So there are 5 layers here. That's a weird looking bracket. Okay, Maybe I'll start from the outside. On the very outside, I have a cosine function. Inside the cosine function is a square root function, a radical function. Inside that is another cosine function. Inside that cosine function is a tangent function. And inside that tangent function is a linear function. There's 5 layers here. So if we didn't see that, we would for sure make a mistake. And a common mistake is to miss a layer. That's it, starting from the outside in. So I'll write this as dy dx. So the derivative of the outside layer, the derivative of cosine is minus sine, leaving all of this as is. So square root of all right, step 1 done. Times. The next layer is the square root function, which maybe I'll pause for a moment. Just give myself a bit of space. That didn't work quite like how I wanted it. No, that's not what I want. You little, you're gonna listen to me? There we go. Okay, so for the square root part, I would actually recommend, before I go on, to rewrite my original function as the cosine of all of this good stuff to the power of 1/2. If I write it like that, which is completely equivalent, it makes it more, I think, clear how I can use the power rule to differentiate this square root part. So to differentiate the square root of all that, I'm going to think of it as a power of 1/2, which means I can use the power rule, so times by 1/2 of, again, all of this stuff here. To the negative 1/2. All right, times, what's next? Another cosine function. So times minus sine of what's inside left alone. So I'm getting, notice each layer, what's left inside keeps getting simpler and simpler. We're kind of working our way in. All right, so now I've differentiated the cosine function. Now I have to differentiate the tangent function, which is going to be secant squared of pi x. And the very, very final step is to differentiate that very inside function, which is pi times x. Since I'm differentiating with respect to x, pi is like the slope of the linear function, so the derivative is just pi. Well, I don't really need to put brackets there so much. I want to make it clear about what's what. And so notice I said there was 5 layers. Here's the first. Here's the second. Here's the third. Here's the fourth. Here's the fifth. Didn't even fit on my page. And now at this point, and for most of these, like right now, really the focus of the vast majority of this unit is just the process of differentiating a variety of functions and relations. So while I could clean this up, that's not really what I care about. Okay, what I really care about is that we just understand this idea. In this case, I'm sure there's a few things I could do to clean this up a bit. However, I want to finish off by going right back to the start and something I kind of didn't mention. And that's this part right here, which is another way of thinking about the chain rule. And so, for example, here, if I want to find the derivative of a function, but that function has, for example, let's say function y is a function of u in itself. It has like a function u inside it. So what we're really doing every time is we're finding the derivative of the outside function with respect to u being the inside function, and then we differentiate the inside function, u, with respect to x. And if you visualize it this way, you can kind of almost visualize that these cancel each other out, and it's the same as dy dx. However, again, in practice, this doesn't really matter right now. This becomes more important when dealing with integrals, which is the other side of calculus. But essentially, this is the exact same idea. And like I said, especially if you have just 2 layers, the first step is you are differentiating the outside function with respect to the inside function. And then you differentiate the inside function with respect to x. And the idea here is that this u is the inside function. Why u? I don't know. Why not? But this idea of thinking about u as being an inside function will come up again later on in integrals. All right? But for the time being, it's really more about just getting a sense about how this works. So I wouldn't get too hung up on any of this right here. I would get hung up on understanding these steps here. And that's where I'm going to stop for now. But